The analytical methods in solving systems of linear equations are Gaussian and Gauss-Jordan eliminations. Check how Gaussian elimination without pivoting is done here in numerical solutions to CE problems. Gaussian elimination is one approach in solving systems of linear equations. This method uses half of the solution by creating a triangular matrix, then computing for the values by algebra. In transforming a matrix, extract the coefficient of each term and arrange them in an augmented matrix. What do we mean by Gaussian elimination without pivoting? Pivoting is the manipulation of the equations or rows and even columns to rearrange the terms in a matrix. The approach using row operations exclusively is termed as partial pivoting, and the other approach, which moves rows and columns, is complete pivoting. For Gaussian elimination without pivoting, the distinguishing marks are first, the rows are never interchanged. Row operations are generated using the original location of the equations or rows. The problem for the first example has four equations with variables x, y, z, and w. In order to start with Gaussian elimination, the coefficients of the system are placed in an augmented matrix. This is a matrix where coefficients are placed in one side, and the constants are also placed on the opposite side of the matrix. Create a triangular matrix, and that is starting with the first column. Use the first row in zeroing out the first elements of the other rows. In this example, zero out 4, 2, and 3. Let's zero out the first element of row 2 using the first row through 3 times row 2 minus 4 times row 1. The first element is 3 times 4 minus 4 times 3, which then is 0. The second element is then 3 times 1 minus 4 by 4, which is negative 13. The third element then is 3 by 1 less 4 of negative 2, which is 11. The fourth element is thrice of 1 minus 4 by 1, which is negative 1. The constant is then 3 times 13 minus 4 times 9, which is 3. After the second row, continue zeroing out elements of the first column, that is from the third row by using the first row. The new third row is then 3 times row 3 minus 2 times row 1. The first element is then 3 times 2 minus 2 times 3, which is 0. The second element is thrice of negative 1 minus 2 times 4, which gives negative 11. The third element is 3 by 3 minus twice of negative 2, resulting to 13. For element 4, 3 times 2 minus 2 times 1 is 4. And for the constant, 3 times 17 minus twice of 9 is 33. Now we have zeroed out two elements under column 1. There's one more from row 4. Since the values are both 3, we create a new row 4 by subtraction between rows 4 and 1. The first element is 3 minus 3, giving 0. From the second element, 2 minus 4 is negative 2. The third element, 1 minus negative 2, gives us 3. From the fourth, negative 1 minus 1 is negative 2. And the constant yields 6 minus 9, which is negative 3. This completes the procedure for the first column. Now we proceed to the second column. Use the second row as the zeroing out row, also termed as pivot row, And we are to zero out elements from the second column under row 2. That is elements of -11 and -2. From row 3, the operation is 13 of R3 minus 11 of R2. The first element is then 13 times 0 minus 11 times 0, which is 0. The second element has 13 of -11 minus 11 of -13, giving 0. The third element has 13 times 13 minus 11 times 11, which is 48. The fourth element is then 13 times 4 minus 11 times -1, giving 63. The constant then is transformed from 13 times 33 minus 11 by 3, which is now 396. To zero out the bottom element of the second column using the second row, the operation is then 13 of row 4 minus twice of R2. The first element is 13 times 0 minus twice of 0, which is 0. The second element is 13 times -2 minus 2 times -13, which also gives 0. For the third element, 13 of 3 minus twice of 11 gives us 17. For the fourth, 13 times -2 minus twice of -1 results to -24. And for the constant element, 13 times -3 minus twice of 3 is -45. To complete the upper triangular matrix, we still need to zero out one element at the bottom of column 3. This is done by using row 3, and the row operation is 48 of row 4 minus 17 times row 3. So the new row 4 then is transformed starting with the first element, having 48 of 0 minus 17 of 0, which is 0. The second element is 48 times 0 minus 17 of 0, also resulting to 0. The third element is 48 times 17 minus 17 times 48, which is then 0. The fourth element is 48 times -24 minus 17 of 63, giving -2223. Then the constant becomes 48 times -45 minus 17 of 396, which is then -8892. Having completed the upper triangular matrix, we then employ back substitution to identify the exact values of the variables. Take note that each of the columns of the matrix is designated a variable, that is x, y, z, and w columns for this example. Starting from the bottom row, we see the equation of -2223 as equated to -8892, which then gives w as 4. From the third row, the equation is 48z plus 63w as equated to 396. Plug w of 4, making the equation 48z plus 63 times 4 as equal to 396. By transposing, z then becomes 396 less 63 times 4 all over 48, and z is solved as 3. From the second row, the equation is -13y plus 11z minus w as 3. Substitute solved values and have -13y plus 11 times 3 minus 4 as equal to 3. Extract and solve y, giving 3 plus 4 minus 11 times 3 all upon -13. So y is equal to 2. Lastly, solve for x from the first row, with the equation 3x plus 4y minus 2z plus w is equal to 9. Plug in known values and have 3x plus 4 times 2 minus 2 times 3 plus 4 as equal to 9. Extract x to have 9 minus 4 times 2 plus 2 times 3 minus 4 all over 3, giving x as 1.